Now we have a talk from Mitra from University of Southampton, who's going to be talking to us about synthetic data.
Thank you very much. So thank you, Mark, for inviting me to present here. And I'm going to be talking about, as Mark said, synthetic data as a method for protecting confidentiality. Yeah. Okay. So I'll first give a very sort of brief introduction and sort of give an overview to synthetic data. How does it work? I'll then talk a bit about administrative data, where we're going to be sort of considering synthesis as a method for protecting confidentiality. And then I'll give some preliminary results based on an application to a particular data set we've considered, and finish with some concluding remarks. And I should say that this is a very applied talk and applications-driven talk. Okay, so agencies such as the ONS wish to release useful survey data to the public, but they also have to protect the privacy of respondents. And so a confidentiality risk occurs when, through statistical matching, an intruder can identify an individual in the dataset, and or sensitive information is revealed about that individual. So an intruder might possess some information about someone, and then thinks that individual's participated in a data set, in a survey, let's say, and so they try and match the information they have to the information that's given in the data, and if they can find matches, then there's a good chance they could find that individual and then learn maybe some new information that it didn't know about the individual that it reported in the data set. I think we're all familiar with that. And so these confidentiality risks are possible even in large anonymized survey data sets. So I realized that I've used the term anonymized, and I'm sure, given the theme of the talk, what I mean by anonymized here is simply just removing unique identifiers, so things like name, date of birth, national insurance number, that sort of thing. I should use a different term, which I can talk to Mark about later. So this gives rise to statistical disclosure control methods, which alter values in the data to protect confidentiality. Okay, so just to give a little bit of motivation about why I think synthetic data is a good way to proceed over what perhaps been done before, is that these sort of traditional SDC methods that have been around for a while, such as sort of recoding, where you sort of release data at a higher level of aggregation, reduce the amount of detail in the data set, or additive noise or swapping, is that they all sort of start with this premise that they're going to damage the data, right? You know that you're going to make the utility of the data worse as you apply that method. And the more you apply it, the worse the data is going to get in terms of utility. And so the question then becomes, how much damage to the data can we do before either the data becomes safe for release or before the data just becomes unusable? But synthetic data is, I think, a bit different to that in that it doesn't start with that premise, right? So synthetic data proceeds by assuming that it is possible to generate a simulated accurate representation of the original data from some appropriate probability distribution, say, that users then can use to learn equivalent information from. So a simple example is you've got a survey, let's say, of just two variables, income and age, say 1,000 individuals. And as an analyst, I don't really want to learn what an individual person's income or age is, right? I want to learn about the joint distribution of income and age, right? So provided the mean of income, the mean of age, if I were to fit a regression of income on age, if those coefficients were the same in the synthetic data as opposed to the original data, that would satisfy me as an analyst. It doesn't matter if the values in the data aren't the same as what was original, right? So that's where the nice thing about the motivation of how synthetic data can work. I think it's quite a useful way to think about it. Okay, so briefly, how does synthetic data work in essence? So it works by modeling the relationships between the variables in the data set, and then using that model, we replace or impute, depending on what term you like to use, values in the data using their predictive distributions. And that creates what's known as a synthetic data set. And then you do this multiple times to generate multiple synthetic data sets to take account of uncertainty and imputations, so that the released data are a mix of observed and synthetic values, so you've protected confidentiality to an extent. The released data look like the actual data, so they've got the same structure, format that the original data had. And provided you've used an appropriate synthesis model, the statistical analyses valid for the original data would also be valid for the released data. And because you're doing this multiple times, typically that's how the approach was framed. You have multiple data sets, but there are some quite straightforward combining rules that you can use across the synthetic data sets to obtain appropriate inferences. But for interest of time, I won't go into them, but they're normally quite simple to apply. Okay, so brief illustration. Let's suppose you've got a data set with two variables, x and y. Let's say y is some sensitive variable, maybe it's income or something that you want to protect. And there might be some individuals that are sort of more risky than others. So maybe some individuals just have really large incomes that you want to protect. And so in that setup, you just synthesize these people's incomes by forming a model that relates x to y, and then you just use that model to impute or synthesize their y values. And you do that multiple times here, 3 times, and each one is a synthetic data set now. And so this is what's called partially synthetic data, because only a part of the data has been changed. Okay, you can sort of be more extreme, and you can synthesize a whole variable. So let's say I want to be really conservative in terms of protecting risk and synthesize the whole y variable. You can do that. Again, do it 3 times here to generate 3 synthetic data sets. And something else you can do, which is done in this round, is just to say I want to protect the whole data set even more by just fully synthesizing the data. So here I synthesize both x and y, and that's what's called generating fully synthetic data sets. So again, you do that 3 times here. Okay, so that's synthetic data. We're looking at administrative data in our example here. And so, what's the motivation for doing this? Well, there's this, relatively recently, the government has started this initiative for open data, and what it means is that government departments are trying to make versions of the databases it holds more accessible, or at least some versions of them. And it's obviously clearly a challenging problem for some government departments, because the data sets they hold are quite sensitive. Okay, so why is this happening? Several reasons. You can think of as lots of reasons, I suppose. One thing is there's this ONS census transformation program that's looking at ways to enhance the statistics from the next census, the 2021 census, and improve annual statistics between censuses. So one way would be to use administrative databases to supplement information from the census. Another thing is that these databases already exist, and they're there. And so, rather than having to commission costly sample surveys, which do cost a lot of time and money, why not just sort of make this data available, because there could be potentially useful information that researchers could analyze and use. So why not release that? And then, of course, government transparency is also important too. Okay, well, obviously you can't just simply release that data. It's quite confidential. So, the data holders and the public need to be satisfied that any released data is safe. Unique identifiers obviously need to be removed, but as we know, we need to do some sort of disclosure protection to apply them to those data sets as well. So this is where synthetic data offers an appealing way forward here, and the ONS has held various workshops to consider potential for this. Okay, so what are some of the challenges when you sort of look at this? So, well, one thing is the original framework for synthetic data was proposed within traditional sample surveys and censuses, but these data sets are different to those. So some of the usual measures of assessing maybe risk and utility might not be appropriate. So, one thing is survey samples have nice survey weights and survey designs, while these administrative data sets weren't designed with that kind of type of analysis in mind. The other thing is that these data sets are quite large, and many traditional methods might struggle to work properly on these data sets. Okay, so we're going to focus on a particular administrative data set called the school census data. Just a little bit of background. The census is split into the English school census and Welsh school census and contains lists of all pupils attending state schools in these respective regions. So at the time that we started this, we couldn't actually get access to the original data. There's all sorts of confidentiality things we had to go through. So we actually created some dummy data, but it's very carefully constructed. So it's not just sort of done very quickly. We did quite a good job, I think, creating this dummy data. But it is dummy data, so I should need to make that very clear when you see the results. So it's taken from only public sources. There are various websites here that I give where we created the dummy data set, but it is just from all publicly available sources. I should say that we have relatively recently now got similar results. I've got results from some of a sample of the original data, and well, suffice it to say that results you see here are by no means completely irrelevant. I mean, so there's merit in looking at the results that I present here. Okay, so dummy data contains data on various variables, including geography, some measure of, so this is at the local authority level, ethnicity, age, sex, language, and school phase. Key point is we're all categorical, so that has some complications, that you'll see in a minute. It's a very large data set, so as you would expect, it's a census data, so comprising approximately 6 million units. But if you think about it, if you look at the number of levels that each of these categorical variables has, the number of, if you think of the data set now as a multi-dimensional contingency table, because it's all categorical, so that table has a lot more cells than there are observations. So it's a lot more than 6 million cells. So that, if you think of it from a statistical point of view, that makes modeling quite challenging. So we're going to consider some preliminary results after applying some synthesis methods to this school census dummy data. So we focus on synthesizing initially the first 4 variables, geography, ethnicity, sex, and age. And we just synthesize them in a sequential way. So you've got this joint distribution you want to synthesize to determine and then generate synthetic data from. But in order to do that, we'll just do it in a sort of a univariate way, in a sequential way. So we'll first synthesize geography, and then given geography, we'll synthesize ethnicity, and then given geography and ethnicity, we'll synthesize sex, and so on. And where each of those conditional models is going to be sort of determined using an appropriate regression model. So remember, the data sets are really large. So even if you go to the second sort of this, even if you go to this second step here to fit a regression for ethnicity on geography, and typical one is a multinomial logistic regression, that just becomes infeasible in terms of fitting it in many statistical software packages. So we were using R, and it was just wasn't working for us, and it's computational really. It's basically that with just so many parameters in that model it has to estimate. It just really struggles, and it'll just get something that'll get even worse as you go down the list. So what do you normally do here? Well, one of the standard approaches is just to consider splitting the data into some subsets, but that's not that ideal. I mean, it's often going to be arbitrary, and it'll just get worse and worse as you go further down the list. So, and also, this is a computational problem. It's not a mathematical or statistical problem that we're encountering. So it'd be nice if we didn't have to do that. So we actually managed to get around it by using what's called iterative proportional fitting. I don't have really the time to go through exactly how it works, but it's essentially used to estimate cell probabilities or frequencies subject to log linear constraints, which correspond to preserving margins of a table. And it works well in large tables with lots of cells. So it's basically an alternative way that allows us to get cell probabilities and so forth, which are then essentially the same as getting the parameter estimates. So it's a different way to estimate parameters, but you still get the equivalent parameters out using this method. So it was nice that worked, and it basically ran relatively quickly as well, even in these quite complex problems, which was good to see. So we now can go ahead and synthesize the variables from a joint distribution. Synthesize first geography, like local authority. That's quite easy. There's no conditioning there, so we just use quite a straightforward Bayesian model, like a multinomial Dirichlet model, to generate synthetic geographies for all the data. And then we go forward and do all the regression modeling through multinomial regression models, where they just fit using the standard multinomial logistic regression, where iterative proportional fitting was used to obtain fitted probabilities, where the constraint we put in was preserving two-way margins of tables. And then we can actually now see some results, so we'll consider some graphical diagnostics. So I hope this can be seen clearly, because I don't know how well it displays, but basically the first panel just presents this is just focusing on after synthesizing geography. So once we synthesize geography, we look at diagnostics, and we'll look at the counts, synthetic counts versus observed counts in the left panel. So you can see that the fitted line is the y equals x line. So you can see that for each local authority, you look at the synthetic count in each local authority versus the observed count, and you just like them to lie on the y equals x line, really. And you can see that they're doing a pretty good job of that. I mean, there's some variability there, but they are, by and large, lying on that y equals x line. Perhaps more informative is this plot, which is looking at the percentage difference between synthetic and observed counts against the corresponding cell size. So if you think about this, if you think about it from a confidentiality point of view, if you've got a cell with a lot of people in, so that's like 200,000 in that particular geography, you're not too worried if a synthetic count is very similar percentage-wise to that original value, because there's so many people there, right? So it's not really, we're not worried about that in and of itself. But if you come to the smaller cells, we have people with very few numbers of people in those cells. You'd want the synthetic counts there to be not too similar to their original values, because then if they were very small cells, then you might be able to or from a confidentiality point of view, you might worry. So you kind of want a sort of a funneling effect. That was what we were looking for, and we can kind of see that here. It gets a bit clearer when you go to the next plot. So after synthesizing ethnicity, we can sort of break it down even more. So you look at all the synthetic counts for every given pair of ethnicity and local authority. So you have more cells now because you've got you've got two variables now you're looking at, and the cell counts will in general get smaller as a result. And you see again you've got this nice plot here where all the synthetic counts lie nicely in the y equals x line. So synthetic and observed counts are being preserved, and then here when you look at the percentage difference between the synthetic and observed cell counts, you see that for small cells, there's a bit of variability going on, but for the larger cells, you're staying pretty close to what you'd like to see. Okay, just some further diagnostics. There's lots more we can do, but in the interest of time, I won't go through them all. We looked at some of the small cells because we're worried about some. These are interesting for confidentiality reasons. So zeros, for example, means the cells with no one in, and ones means the cells where there's only one person in, and so forth. And so the first and second row present the proportion of cells for a given cell size in the synthetic and observed data, respectively. And we can see, for example, that there's lots of zeros in this synthetic data because there's the way that it is. There's so many cells, and there's not that many people relative to the number of cells. And so, 68% of cells were zero in the observed data, 69% were zero in the synthetic. And you can see sort of profiles going across for the other cells. So they're not always the same. They're not going to be the same, but they're not too far off either. The third row is interesting. That was sort of, again, looking slightly from a confidentiality point of view. It's basically the proportion of cells of a given size in the observed data that are synthesized to have the same cell size. So look at the zeros, basically it's saying out of all the zeros but in the original data, 96% of them were synthesized to stay zero. So a lot of zeros stayed zero, which you'd expect, there's so many of them. From a confidentiality point of view, the ones is perhaps of interest because those are cells that only had one person in, and you can see that about less than a third, about 31% of cells that were one stayed one. So, from a confidentiality point of view, it's at least good to see there's quite a bit of movement in these small cells, So that's the sort of thing that we've looked at too. And just one other thing, we can sort of think about intuitive measures of risk and utility. So, we could look at them jointly often. So this table presents a proportion of cells that are within p% of their original size. And the first column considers all cells, whereas the second column only considers the non-zero cells. Because you can see the zero cells sort of inflate everything. So you can see that 75% of cells are within 10% of their original cell size, but when you sort of take out the zeros, because there's sort of lots of zeros stay zero, you can see for the non-zero cells about 30% are within 10% of their original cell size. So that's kind of good from a utility point of view. When you go down to like a 0.5%, you might be worried if lots of cells are so close to their original value. And there you can see like 70% do stay within 0.5%, but when you take out the zeros, it's only about 16-17% stay within 0.5% of their original cell size. Okay, so just to conclude, so as appetite for accessing more types of data increase, so do the confidentiality concerns surrounding this. Synthetic data has the potential to handle the challenge of releasing useful survey data that still protects the privacy of individuals. I think some open areas are determining the best way to synthesize different types of data, because that's still new methodology being developed in the area. And from a slightly more practical point of view, it's important to determine how best synthetic data can facilitate access to confidential data. Because, different people view synthetic data in different ways. Some people think synthetic data should be used in one way, and some people think in another way. And I think that's an important conversation that should still be had. Sorry, before I end, I just want to acknowledge the research contract between the Office for National Statistics and the University of Southampton that funded the work, and staff from both organisations who were involved in developing this work.
I slightly jumped the gun there with my enthusiasm to applaud you. Okay, any questions?
I was just wondering, so when you're synthesizing data, if somebody's analysing that, don't they just get back to your generative model? Sorry, maybe there's something.
Yeah, this is the so-called aha factor, that if you just generate data that is purely model-based, you will just return the model. That's true if you were to generate fully synthetic data. If it was partial, like in one of the earlier examples, then you still got a lot of the original data there. It depends what you want from the data again. So I don't think you can say this is going to replace the original data, but could this be a mechanism for maybe learning about a data set before you can get access to it? In that sense, I don't think I'd be so worried about that kind of issue. But certainly, I don't think we can say this is going to be replace an original data set. You know, the original data will still have value. It's just how does this fit into the mechanism of accessing a confidential original data set?
Sorry. Assuming that you can synthesize data in different ways depending on the sort of queries you want to get from the data set, would you see this as a method for people getting access to a data multiple times? So if you have, at the ONS, for example, you hold a data set, and you have various different researchers who want something different from that data set, and ONS can synthesize that data and hand it to them in various different ways. Is that a really intensive process? Do you think that's a viable method for providing various different researchers with different types of data and so on?
I think that's an interesting way to think about it. I
Summarise
think
the question. We couldn't hear it at all at the
Sorry.
time.
It's basically if you can you synthesize the data for various different purposes. So when you want to synthesize a data set, assuming that you can do it in different ways depending on what query people want to ask of the data set. So would it be feasible for that to be a service for, say, the ONS to provide to synthesize based on the request of a researcher in different times?
I think that's a really interesting point, and I think that is certainly something that could be, that's getting easier to do, because obviously with statistical methodology developing, with things being more easy to implement in standard software packages. So generating sort of bespoke synthetic data that fits a particular purpose. I think that's discussions that we've been having in this workshop, and I think that's certainly something that could be something going forward, because like you say, different users need different types of analyses, different types of different aspects of the data preserved, and so yeah, I think that could be an interesting point.
Okay, thanks, Robin. And just to mention, as Robin indicated, there is a synthetic data group which is formed as a spin-off from the GLA program, and we're in the process of producing a position paper which I've already published. So watch this space. Okay, so now next.